All right. Thank you very much for the kind introduction. Hello, everyone. I'm Sunita Chandrasekaran from the University of Delaware. And for those who haven't heard of Delaware before, it's in the Northeast. It's bordering New York, Maryland, Philadelphia. So that's the part in the US. And to acknowledge and honor the Maori culture, and thanks to Florina for pointing me out to the website and to put this together. A little bit greetings in Maori. So I'm from India. Yosemite is my mountain, Ganges in India is my river, and my surname is Chandrasekaran, which Nicholas did a perfect job in pronouncing. Thank you, Nicholas. And a little bit on the side, besides while I love my work and stuff, I also started painting a couple of years ago, say 4 or 5 years ago, and inspired by the application that you will hear about, which is plasma physics, I painted this with acrylic and gouache. And the premier supercomputing conference in the US that happens every November was so kind to accept this and display as a part of Art of HPC. And if you all go to Scholl's Darkstuhl, where the computer science math events happen, I told them if they would like to take it, and they were willing to take it because I've seen scientific art on the walls of Darkstuhl. So that's what I do on the side. And so it's a scientific representation of a laser particle accelerator. So that's what is happening. The blue part is the gas chamber, and the lots of different colorful particles you see are electrons, and they are just emitting that kind of energy, and thus creating this high energy laser particle accelerator, which is what the application is all about. A very brief intro about my group, Computational Research Programming Lab back at the University of Delaware, a bunch of PhD, masters, and undergraduate students, where we do both foundational as well as applied computer science, meaning building compiler runtime implementations on programming abstractions of OpenMP and OpenACC, directive-based programming model, as well as apply some of these abstractions to real-world problems, because then it makes you go back to the drawing board and find out what are the gaps in fundamental computer science. So it tries to do both ways. And the best part of working with interdisciplinary scientists is you get those pretty pictures with jiggles and moves, because otherwise computer scientists will give you tables and figures and numbers and black and white images, which might be slightly boring. And thanks to all the funding organizations, just wanted to point out LIDARs. We all go through airports, and the scanning machine, next time you go through Auckland or Christchurch, you will see the machine on the top, you'll see the label LIDARs, which I started noticing after I got the funding from the Biomedical Research Center off of NIH and Frederick National Lab of Cancer Research. So that's a background for LIDARs. Okay, so piggybacking on Alok's talk and several other talks we have heard so far on the abundance of data, complex streams of data. And no matter how wonderful the machines are and how massive the storage capacities are, you still get stumped because you're dealing with terabytes and terabytes of data, right? So how do you maneuver the file system? How do you maneuver and analyzing this complex streams of incoming data and still be able to answer some of these scientific questions? So that is setting the motivation of this talk, which is an interplay of both high-performance computing, in-transit data analysis, machine learning, thus eventually also being able to answer a scientific and a computational question. So data, of course, you have seen data in different fields. That is an image from ChatGPT, which I'm not very impressed about, but since I've burnt some trees, I thought I will add it anyway. Of course, I have to work on my prompts clearly. But the idea was to represent, climate, weather, and all the patterns happening in our on Earth, just to represent the different Earth system models, different, applications, and I'm sure I'm missing a bunch there, to mention the abundance of data that we are dealing with, literally every real-world scientific application, right? So the question or the topic of interest in respect to dealing with this complex stream of data is what we were looking into is the area of plasma physics, which is governed by the physics of charged particles, that is diverse data properties, and several simulations takes millions and billions of particles. And the particular phenomena that picked our interest is the plasma instability, phenomena of the plasma physics code. Now, what do we mean by plasma instability, right? So we see northern lights, we go, aha, that's beautiful. But what's causing northern lights? Some of the plasmas escaping the magnetic field. And the plasma escaping the magnetic field is not necessarily a good thing because it can damage nuclear reactors and fusion research, for example. So how do you put a pin on where is this instability in the plasma physics even stemming from? So that's the question we wanted to ask, right? And we are dealing with, again, tons of terabytes of data. So these are some examples of, the repercussions of plasma instability. What we wanted to learn is reconstruction of phase space from observations to get a detailed view of the growth and dynamics of the plasma instability. So how do you map the output back to the input and reconstruct this instability region? If we did not do this, we're looking into all these correlations and computations of all this, which is going to take extensive post-processing and analysis, which would take years, no matter how compelling machine you have. So basically extracting meaningful info out of complex, heterogeneous data generated from either simulation or experiments. So you can imagine the influx of that much data, yet put a pin on the instability region. So my team is large. Majority of them is across a little pond from the US and Germany, in Helmholtz-Zentrum, Dresden-Rosendaorf, HCDR, which is a national lab in Germany. We kicked off this project around 2019. So today's version is a squished version of 4 or 5 years of HPC plus ML work. And many, many thanks to HPE and AMD, a center of excellence, as part of the, who are involved in, obviously, in building the world's second fastest supercomputer, Frontier, without whose help this work could have never happened. So a brief video of, the painting that I did was inspired from some of these ideas where, again, you see the blue chamber, which is a gas chamber, and you see the laser pulse, which is the golden thing that is staring through the plasma chamber, displacing electrons. It's creating positive and negative charge regions, and it's creating a wake, which is what you see along these little lines. That energy is in turn accelerating this laser plasma, thus creating this high energy laser particle accelerator, right? So an analogy could be you are in New Zealand, you're in an island, you could be in a lake with a cocktail in your hand, and it might be a cruise which is cruising through the water. It's creating ripples, and imagine surfers are jumping onto those ripples, and because the cruise is going at its speed, it's accelerating the surface, right? So the lake is the plasma chamber. The cruise is your laser plasma, and the wake, and then there is a surfer, which is where the laser plasma accelerator, high energy accelerator is created. The applicability of the SPIC-on GPU code itself is multifold, in physics as well as applications in radiation and cancer treatments, because your goal is to have this really high energy accelerator that can only target the cancerous cells and not the healthy cells around it, which is what leads to several side effects out of chemotherapy, for example, right? So your goal is to get how high energy can you get? Perhaps right now it is in giga-electron volt. How could you get to tera-electron volt to the extent of this accelerator? This kicked off as a challenge program when Frontier was being built back in 2019. Oak Ridge has this program called Center for Accelerated Application Readiness, CAR, where the goal is to stress test hardware and software of the Frontier system. So anything that you think can go wrong would go wrong, right? And we worked from the baby Frontiers like pre, 2019, 2020, 2021, 2022, around the time frame of 2022, 2023, when we had the real Frontier deployed. So you work with different versions, MI50, MI200, MI210, leading up to MI250, right? And you can imagine everything that went wrong, went wrong. The goal was to get 4x performance compared to the baseline, which is from Summit. This is just the HPC angle, the computational angle. We'll get to the scientific angle in a little bit. So we wanted to see how the code can be improvised, not lose performance, keep it portable, and still meet the 4x challenge and observe all the issues that would have stemmed in moving a code from an NVIDIA system Summit to an AMD beast that the code has never seen before, right? The PIC-on GPU code has a good history of having run from Titan K20s to V100s to A100s, all the way to a couple of nodes of Hopper 100s, 200s. So it's all a green system. And now you're throwing it, about a 38,000 AMD 250X GPUs, and you're saying, let it run, right? So the fun part is, how do you get it run? This was another Oak Ridge test bed with some Ampere computing system, and the code was a 2013 Gordon Bell runner-up. So very briefly, I'm sure we all here know what the system is, looking at X number of cores, X number of GPUs, and something to take away is 4 AMD 250X is actually 8 GCDs, right? So 1 250X is 2 GCDs. So there are 8 GPUs you can target, 8 GCDs you can target in a particular system. So that's, you would think it's an obvious detail, but the very first time when the machine was up and running and you ask for nodes, you get GPU, but it's not a GPU, it's a GCD. So often we thought we got 4 GPUs, but actually we got 8 GCDs. So there was such trivial info that, if you look past, your calculations can go wrong. The exascale challenges, obviously, with Picon GPU are multifold. You can't lose portability because it's not the only system you want to run your code on. You want to achieve performance. You want to make sure your code is scalable. And of course, you can see all the pretty images, right? The team was trying to generate off different GPUs. Visualization is key to visualize the science behind the Picon GPU. And of course, workflows. I'm sure Rafael will tell you more about the complexity of workflows as we go forward. But all of them had to come in together for the code to run on such a massive system. The underlying software stack that allows Picon GPU to portably run on multiple varieties of system is Alpaca. You never heard me say this while it is being recorded. Alpaca is a European version of Cocos. Forget it, I never said it because both teams will not agree with me. But it's a C++ meta programming. And it allows all of these underlying portable backends. And while we accepted the car challenge, the backend for HIP, right, an OpenMP 4.5 offload, as well as an AMD NVIDIA GPUs and SYCL were being implemented as we speak. So many of the implementations targeting AMD GPUs kicked off after 2019. So that's the baseline, right? This is from 2019, November, Picon GPU running on Summit. This is your form equation, and the idea is to get 4x times 16.3 teraupdates per second on Frontier, right? That's, again, a computational challenge. Peak and sustained power was so on and so forth. So this was our baseline where we started. And as we went, 2020, 2021, 2022, there were a lot of improvements, not only on the science part, but also on the computer science part, right? So there is code updates, laser functor, the new field background. This laser algorithm alone took 2 years. So going back to Alok's talk, where the science communication is so important, I cannot emphasize further. Because a physicist would tell you about plasma instability, and I'm like, what do you mean by plasma instability, right? So in order to appreciate what you did, it took so much back and forth with the physicists and the computer scientists and PhD students, research software engineers, to appreciate the problem before you find the solution. And that is so important before you just jump in and run a program, because then you're working in void, right? You're not appreciating what you've done. So these were some of the computational improvements, and we always joke that this Red Queen's race because you can't keep up, because everything is evolving. The ROCm stack was evolving, the hardwares were evolving, the input-output workflows were evolving as we spoke, so everything needed to be updated. Alpaca needed to be updated, keeping up with ROCm backend and so on. So imagine the amount of bugs and issues, imagine the amount of phone calls, text messages, texting AMD with a GitHub number that I need a fix for this because I can't move. You would think you can work around and get that thing fixed, but that is not a sustainable solution. Your code will work, but you did not help the community because somebody else is going to run into the same bug and they're going to file the same issue, right? So our goal, or at least my team's goal, was workaround is fine, but this must be recorded on GitHub. This has to get on the HP, AMD, and Oak Ridge dashboard. So the issue is there, and the vendors are working on it. So it is a sustainable solution and not like a quick fix. So that was usually my takeaway, that hardware is great, but it's only as good as software can get. And I think we've been hearing a lot of it, including from the panel last afternoon. And the communication is so important as we build these bigger machines because there are multiple stakeholders behind besides just the application developer, right? So there were some brouhaha moments where this was the baseline, right? We started there, and of course, this is projected because imagine all the backward dependencies. The code is improved. Summit has some software versions. Our code is in a different version. You can't possibly run without running into bugs. So that's projected, and somewhere around Frontier's 8,000 odd nodes, we met the card challenge. So drum roll, right? And then we got to even run it up to 9,216 nodes when we had some more allocation. So the challenge was met. This was a really, really happy moment for us that we were able to, get the entire software stack up and running on the Frontier system. So the challenge code was single precision. For double precision, we even saw 8.5x. The replication of the previous chart that you saw, this is all on Frontier. That was a peak figure of merit, 78.3, with some sustained peak power of 23 megawatt. I'm not sure I'm going to be happy about this, but because it takes so much power, but it's good to see some applications running at 23 megawatt. So we call it a happy moment, but that was not a happy moment for us. We wanted to go back to the code and see power optimizations that you could do so you burn less trees, right? So that's the average power, and this is all the configurations on Frontier compared to Summit. So obviously you could do more science. That's a no-brainer. This is weak scaling, no surprises, ran pretty well. Scaling from 48 to 73,000 GCDs again, by 2 is the number of GPUs you have on Frontier. So X number of GPU utilization, great. So then we came back to the drawing board to ask, what scientific question have you really answered? We have answered a computer science question. We were able to go back to the vendors and work with them and solve a bunch of software problems, great. But how did it solve a plasma physics problem? It actually did not, right? So while I was celebrating with my computer science hat on, the plasma physicists were sad because they were like, this doesn't do anything much for us. Okay, so what else can we do, right, to answer the scientific question? The issue of why they didn't have the aha moment is the thing is not to run things fast, but the thing is to explore varieties of parameters, configurations, right, to answer those compelling questions that you have in the scientific area. So larger parameter range, which needs a much more sophisticated workflow to be able to answer the plasma instability question. So we kicked off some conversations over there, coming back to my original motivation in the beginning of the talk, where we're dealing with terabytes of data, right? And while Frontier is awesome, there is a limit to the storage capacity. So what do? Putting the question back again on the table, instability, reconstruction of the output back to the input, put a pin on where the instability is coming from in the plasma physics code. So that led to this idea of HPC. We did that part, great, but now let us look at that. Let us look at the data streaming. Let us do some learning, and then find out what were the machine learning outcomes. So there is a in situ data analysis, machine learning coming into picture at the moment, right? So the application for this particular case study is the KHI instability, where well-known shear surface instability observed in fluids and plasma, say wind and water, when they are married together, right, you see some effects, right? So that's the shear surface, that's the chi that we're talking about. So 2 layers, different velocity, different density, and you see the colors changing here, and it changes depending on how much there is radiation of these electrons. The thicker and brighter the colors get, the more the acceleration the radiation is. So we chose this as a case study, and all the visualizations are via this ISAC tool, open source, running both on NVIDIA and AMD GPUs. Hats off to Richard, who is also HCDR Germany, who is reproducing these viz on both AMD as well as NVIDIA GPUs. We used OpenPMD, ADOS2, you might be aware of these, where OpenPMD is a data standard for particle mesh data. ADOS2 is where you try to deal with the input-output and try to communicate between different nodes. So these are all established works. So a lot of collaborators there working with Oak Ridge Berkeley Lab on connecting the OpenPMD ADOS2 with our code, building the ML model, doing the in situ analysis, data analysis, learning, and then delivering the learning outcome. Fundamentally, the challenge was that's the terabyte of parallel throughput of particle data we have for the code, right? And the Orion file system on Frontier bandwidth was 10 terabyte. So Picon GPU scaling to just 25% would produce 1 petabyte of data every time step, right? And then thousands of time steps with each lasting of 0.1 to 1 second, you're already looking for 10 exabyte storage capacity. That's not practical. You just can't increasing the storage capacity. So the implication was the entire file system it would be exhausted in 100 to 1,000 seconds, which is not okay. So that led us to exploring how do we, in transit, how do we have this stream of data transiting through the nodes of the entire system, and you learn on the fly, right? So there are different ways to do this. We have only so far targeted the producer-consumer model, where producer is the streaming of data, consumer is the ML application. You circumvent the storage, which means nothing goes through the storage, but the data is just streaming through, and the consumer, being the ML app, is picking up the data and doing its ML model. And this is all within one node. So some GPUs doing the streaming, some GPUs doing the learning. Now you can imagine some nodes doing streaming, some nodes doing the learning, and then you mix it up, mixture of intra plus inter. Those are configurations we haven't tried, but just thinking about the intra made us think, oh, we could do a couple of more scheduling strategies here, opens up several PhD theses. So these are some more examples or runs of the entire system, trying to experiment with MPI and libfabric of how much of per node throughput is even possible, because that's our target. This is our target, but these were some experiments we did. At this point, the consumer was not an ML app, more of a dummy consumer, but the producer side, we were trying to see how much of these nodes can really consume. What we did was continual learning, where you don't store data every point in the disk, but you circumvent the lack of adequate disk capacity, and you still learn along the fly. So that leads to the ML application. There is a lot going on, but the bottom line is it's an ill-posed problem. So we came up with an invertible neural net architecture. There is an encoder, there is a decoder. You see max level perceptrons, you see max pool. Basically, the particle configurations were represented as a point cloud net. And you have these different layers which are trying to reduce the dimensionality, get to the latent Z vector, but the INN is not going to exactly replicate the latent Z hash vector, because the backward pass is only going to give you a variation of the input particles, not all of the particles, which means a decoder is not going to follow this, because every time INN is going to give you variations. So we adopted a variable autoencoder model within the decoder, which meaning you don't want the neurons to memorize. It's like students doing assignments. They memorize, they solve that problem. You give them a new problem, they're like, okay, what did you ask me to do? So you don't want the ML app to memorize. You want the ML app to learn. So it can, once again, put the patterns and the mapping of output and input dynamically in a robust way. So that there was a lot going on in this entire architecture. I'll fast forward a little bit to get to some of the issues as to why the ML did not quite scale beyond 96 nodes, because again, some of the loss functions we wanted to implement were CUDA-based. So we needed the PyTorch community to make it AMD-based. So you use a bad loss function, for example, the Chamfers distance versus the Earth mover distance. This is what we wanted to use, but it uses kernel operations which only work with CUDA. So there was no AMD equivalent. So we had to use the Chamfers distance, which does not give you the density, the sensitivity of the particle configurations, which means the reconstruction is messed up. You see, so all these were some of the computational challenges, PyTorch ranks taking place, the inevitable all-to-all communication, deficit of 30%, then a lack of availability of PyTorch distributed primitive. So some implementations fell off the cracks while we were trying to solve the computation problems. But while it sounds doom and gloom, the best part is that besides all of this, we were still able to reconstruct partially the vortex region from where the plasma instability was occurring. So that was a huge win for us. It clearly learned to partition the latent space into regions of different flow directions, which is what you see in the little image there. and which both the encoder as well as the INN learn to map. So partial reconstruction of the distribution with ML prediction still clearly identifying the region. So it was partial success, right? The physicists are happy, I'm happy, because they can't be happy easy. You see what I mean? They don't like numbers, they like this. So looking them smile, I'm like, okay, we have done something great, good. So that was a promising first result. And to wrap this up, so that was the overall workflow. But it doesn't end there, right? You can see so many open problems. Fine, we built a surrogate model of simulations of different configurations. But you still see there is a workflow that requires so much attention. There is so many pieces of the workflow that is still not okay. Then there is a reduction of data that we could do without loss of information, so that's a different step. Learning in transit for more than one simulation. Note, this was all one simulation. Now throw thousands of simulations and you can imagine everything else that can go wrong. So more work to do. And I'll just leave this on the slide as the last one, where I think we talked about this. Larry talked about this, and we were all chatting about this as to, can you build customized system per application? I want this beautiful frontier part 2, which will only work for my code, and everything will solve. Is that practical? Not practical, right? We have Slurm, great. But how much of the scheduling can take data coming from all the different simulation experiments, going through data reduction, filtering, analysis, name it, right, with data. Funneling it through all these different levels of the scheduling, trying to learn and trying to, deposit this to architectures. You think architectures are complicated? Think about the first half, right? So hopefully, we are very bright scientists here, so we will have some solutions as we think about this more deeply. But with that thought, thank you very much.